All right, so nice. So let's continue with the question. So part A, write an expression for the PDF of the noise voltage when there is no signal transmission. Okay, so all that, child, let's break apart this first paragraph here. All right, so let's put it into perspective, right? So noise happening, right? Voltage coming in, like actual voltage, you measure in voltage, and based on the voltage that coming in, it will know if it's a 1 or a 0, right? So in the binary communication system, a 1 bit is represented by 5 volts. So if 5 volts come in, they'll read it as a 1, whereas a 0 bit is represented by a negative 3-volt signal, right? So with that, we know that there will be noise in the process, right? When the voltage coming in, you will have some noise in it, right? So we can let the noise be represented by X at T, or it could be N at T. Feel like we use N at T because N at T nicer. So N at T is noise, right? So we'll have a piecewise function coming, right? So the first one we'll have 5 plus noise. We could have minus 3 plus noise, and we could have 0 and noise alone. Yeah? So 5 plus the noise is if a 1 bit was sent. And this is if a 0 bit was sent. And this is if there's noise or nothing was sent. Yeah, so that is the groundwork right here. So we have that going, right? So we could write a nice equation for everything. So R at T is the received signal is equal to S at T, which is the sent signal, which is either the 5, the minus 3, or the, well, 0, I guess, plus N at T, which is your noise. So that is where we get we got these things. So instead of writing X, we could actually write it as R of T. Could have 3 possible outcomes: 1, 0, or nothing was sent. Right? So we have diagram work done. So now the question asks, now we can go back and do the question. Write an expression for the PDF of the noise voltage where there is no signal transmitted, right? So when you have no signal, that means that S at T is 0. So it's basically just N at T coming in, right? It's literally just the noise alone. So now what we could do, we have a PDF equation. So X at T or F at T. So you can write F of X at T of X. Easier to write like that. So it's 1 on square root of 2 pi sigma squared n e to the minus x minus mu n squared on 2 sigma n squared. That is the PDF, right? Because n at t, if x follows a normal distribution fit, it will have a mean of mu n and it'll have a variance of mu n squared. Yeah, so it will be half fit. We end up with this. So mu n and sigma n. So we end up with this piece here. PDF. Right? Did the X to sketch it? Write the expression. Okay, also sketch it. Okay. So when you're sketching it, you have your bell centered about the mu. Right? And then you have your spread. And then you have, you just label it F of X of X. Right? And this is just N of T. Yeah, that's all that part is. Nothing more, nothing less. All right. Right, so part B now. Write an expression for the probability density function of the received signal corrupted by noise if a 1 bit was sent. So, if a 1 bit was sent, therefore R at T is equal to 5 plus noise. Yeah? So, we need two things. We need the mean, and we need the variance. That will never change. So, R of T, we can just write it as R for now, because we don't want to write R at T too much. Is 5 plus, and we can let N at T just be X. All right, so we list the parameter, so X will follow our normal distribution with mu and sigma, sorry, and sigma squared. So we need sigma, we need sigma squared and mu. So the first thing we do, we need to find mu. So it would just be the expectation of R, which is just the expectation of 5 plus the expectation of X, right? Because remember, X is N at T, and 5, well, 5 is 5, and R at T is R, right? That's showing you that, and this is what we're dealing with here. What we're trying to find. So the expectation of a constant, number, expectation of a constant is the constant itself, and expectation of X, which is your mean, so we can write that as, because it's mu, we can say mu R1, represented noise for 1, right? Because E of X is your mean, yeah? And that was N at T. So, no, can't do that. Because N at T already write it as mu N before. So we can't change that now. Yeah, because it's N at T. We can't write a new one for it. All right? Because we had used mu N before, so we had to keep using it. We can't change it up for this one, sadly. So this here will be the expectation of R, or if you want to, you can write it as mu R is just 5 plus mu N. Yeah, so that is how this came about here. Second thing we need is the variance of R, right? So that is the variance 5 plus the variance of X, right? So the variance of a constant is 0. And the variance of X here is just A squared sigma squared, right? That's just from the equation itself, right? So since A is 1 most of the time, you'll just end up with sigma squared N. Remember, this is for noise, right? This part here is the noise. So it does end up with sigma squared N, right? So you have variance of R or var R. So you have that. So basically now we end up with sigma squared of R is equal to this here. So that is what this will end. So now we could put it together into the PDF. So you say f of R1 of X. So it's 1 on square root of 2 pi, and the variance is square root of 2n e to the minus x, and mu, or mu r in this case, is 5 plus mu n squared divided by 2 sigma squared n. Right? And then now to sketch it, the same kind of sketch, just the variance and the mean change. So this here is your mu, I think is mu n, yeah, plus 5. And then the spread is just sigma squared n, sigma squared n. And you have your spread. And you can label it as FR1 or X. So that was that piece, right? So you just start off with the RT, And for simplicity reason, you let R T be R and a T be X. You gotta let it be capital, and if you wanted to, by all means, be my guess. So once you do, you're ready, random variable. So you need to get the mean, so it will be expectation of R, expectation of each of the terms, expectation of constant is the constant, and the expectation X is the expectation X, which you gotta write as mu n, because you know that is the mean for the noise. Therefore, for the mistake I had, keep it as mu n. So I end up with this here. And the variance of the 2, variance of 5, plus the variance of x. So variance of our constant is 0. And the variance of x will be a squared, sigma squared. In this case, a is 1, because the rule is the variance of ax is just the a squared, sigma squared, right? So in this case now what we had, it was just x now. So that is why we could have said a was 1, because it had nothing here, just 1. It was understood. So that is why the a dropped off to be 1 squared, which is 1. All right, nice. So that was part B. Any questions on that one?
Ah.
All right, nice. Okay, so we're going to part C. Well, part C would just be the negative part of it. So write an expression for the probability density function of the received signal corrupted by noise if its 0 bit was set. Okay, so basically saying shalala, but uh, a 0. So it'll be R a T. So that is minus 3 plus N a T. So for simplicity reasons, we let that be R minus 3 and we let this be X. So X follows a normal distribution. So we need mu and we need sigma squared. So the first thing we need is the expectation of R, which is mu R, which is equal to the expectation of minus 3 plus the expectation of X. So this mu R will just equal be minus 3 plus mu n, and then the variance of R. So that'll be the variance of minus 3 plus the variance of X. So variance of a constant is 0. And this is a squared, sigma squared. Since a is 1, let's end up with sigma squared n for the noise. So we now have a mean on your variance. So you could sketch the PDF. So it's minus 3 plus mu n. And you have your spread. Yes, and you could call this FR0 of x. Oh, we forgot to write the PDF. So FR0. So it's 1 on square root of 2 pi sigma squared n. All right, by e to the minus x minus minus 3 plus mu n squared divided by 2 sigma squared. So I repeat it, and I sketch. All right, so any questions on that one?
Nah.
All right, nice. Okay, so let's continue. So we tested C, B, A. All right, so D. Okay, so I you know D gonna be a SATA of C. I'm not gonna do that proof over again, but I just gonna give you the general beginning for it, and you'll continue. All right, because it's a long proof, as you notice. It's the same thing going over and over. It's just the limits will change. All right, so part D, if the receiver, the decision rule is that a 1 bit was sent when the voltage exceeds 2 volts and 0 otherwise. Okay, so what that means is if I was to draw a big bell curve, So we have two things happening, right? Remember, you have a 1 and a 0, and they both have a well, so the x-axis here will be the volts, right? That being interpreted as either a 1 or a 0. Yeah? So you have your first bell shape, which is centered at mu n minus 3. And this will extend, okay, remember it never touches 0, right? And then you have 2, or you can have it as d0 if you want to be technical, right? D0 is 2, right? So this is for a 1, sorry, a 0 bit, right? So any voltage around here will be interpreted as a 0. But now you have the 1, which is centered at mu n plus 5, and that will look something like this. Right? So I don't like how that look. Try to. No. Anyway, why am I overcomplicating this? Let me see how good I could draw that. And these are different color bits. Alright, so I'll work with that. Nice. So we have this going on here. Because of how I draw it, need to change how it overlapping. So it's overlapping right here. And that is D0, right? So you have this going on here. So you have 1 bit. All the values in between here will be interpreted as a 1. And you have the 0 underneath there. Right? So this is what's going on right now. Okay? So you have your 2 and you have the threshold there as 2. So the question said, or the first part of the question, determine the probability that the receiver will indicate a 1 bit if a 0 bit was originally sent. So they want to know if they will see it as a 1, or what if they see it as a 1 if a 0 bit. So we need green, right? So we want a green. But for some reason, we send a voltage that in this range here. So in this range is here. Yeah? Because in this range here, you're in the red and you're more than the threshold. See that? So it'll be in this little piece here. So once you're more than the threshold, you could be interpreted as anything else. Remember, the question said if it's more than 2 or anything else, it will be interpreted as a 0. So in this case, it will be interpreted as a 1. So a 0 was sent. So in this green here is your 0. But if you look at it, this piece here, it could be interpreted as a 1. Yeah? Just looking at that piece. So in this case, what that going to turn out to be is in terms of probability. So you could call that the probability of getting a 1 given that a 0 was sent. Take it right like that. Right? And that will equal to, so you have to integrate, obviously. So you integrate in the PDF, obviously. So in this case, sigma squared. So the integral, so you're going from d0 to infinity. Yeah, because all this, remember this never gonna stop. You're gonna continue going, right? Of e to the minus x. And in this case, you're in the 0. So it'll be minus 3 plus mu n squared on 2 sigma squared, right? So at this point here, we know this is going to end up being half of Earth C of wherever we get at the bottom. Yeah, we know this because we don't care about the other half of Earth C. So what you have to do is the same thing. You let this on the top here, or I forget my dx. Right. So you let this entire thing here be t squared except the minus. I'm not painting the wrong picture. That everything here let it be t squared, right? And then yeah, change the limits. So t squared both sides, you make t equal to whatever, and you just plug in d0 and infinity into it, change the limits, and then differentiate both sides to get rid of the dx in terms of dt. And what will happen is the square root of 2 and the sigma, which you'll get from the square root and the square canceling, will cancel. You end up with 1 on root 2. Integral will be d0 minus 3 plus mu n on 2 sigma squared, I believe. Well, that might be d0, because when you plug it in, your t will be x minus 3 plus mu n on 2 sigma. So in this case, when you plug d0 into it, this part here would just be d0. Yeah? And then once you change the limits and stuff, it will just end up with 1 and root 2, root pi, sorry, square root of whatever d0 minus to infinity of e to the minus t squared dt. And that is a half root c, because we don't care about the next piece. All right? And then now, the second part of the question asks for the probability that they will indicate as 0 given that a 1 was sent. All right, so I'll change the color for this. So you send a 1, for some reason, you're seeing a 0. So that will mean if I send a 1, and this graph here, the red, but if I send a 1 and I get a 0, that means it was here. Yeah? So if I here, it might be seen as a 0. All right, so that there will be from d0 straight down to minus infinity. Remember, the red not stopping here. Can't continue straight. It does get very small. It will go very close to the x-axis, but never touch it. All right, so that will be the probability of getting a 0 given that a 1 was sent. PDF, so you had to integrate the PDF. So sigma squared n. So in this case, you're integrating from d0 to minus infinity. All right, of e to the minus x, and is the 1 bit, so you had to use the mean for that, so it'll be plus 5 plus mu n squared on 2 sigma squared dx. And the chalala for this, same thing. All right, it will end up being the same I that I was going with before. And I'm really gonna change. So I'm gonna end up with being a half of c. All right, and then the final thing they wanted was the total probability error. It would just be adding the two of them together. It would be the probability of getting a 1 given that you send a 0, plus the probability of getting a 0 given that you send a 1. And that'll be the end of that one. Right. So I'm gonna stop it.